Hey there, science fans! Are you ready to dive into the fascinating world of mathematics? Today, we're going on an exciting adventure into the world of calculus, a branch of mathematics that helps us understand changes and motion. Get ready to climb mountains of equations and explore the valleys of functions. It's like hiking through a mathematical landscape. Our mission is to uncover the secrets of extreme values and saddle points, which are crucial concepts in calculus. Imagine a roller coaster zooming up to its highest point and then plunging down to its lowest. These thrilling ups and downs are similar to what we study in calculus. In calculus, we call those high points maximums and the low points minimums. These points help us understand the behavior of functions. Together, they're known as extreme values. They tell us where a function reaches its highest and lowest points. They're like the peaks and valleys of a mathematical landscape. But wait, there's more! Just like in nature, there's more to discover. We're also going to investigate those curious spots on our roller coaster where it seems to hesitate, unsure of whether to go up or down. These points are fascinating. These are called saddle points, and they're just as important as our extreme values. They occur where the function changes direction. So buckle up, math adventurers. Get your calculators and notebooks ready. We're about to embark on a thrilling journey to unlock the mysteries of extreme values and saddle points. Let's dive in and explore the wonders of calculus together. Reaching for the sky. Let's start by picturing a beautiful mountain range. The highest point on a mountain is its peak, right? In calculus, that peak is called a maximum value. It's the point where our function, our mathematical mountain, reaches its highest point. Now, imagine yourself exploring a deep canyon. The lowest point you reach is the bottom of the canyon. In calculus, that's called a minimum value. It's where our function dips down to its lowest point. So, whether we're talking about mountain peaks or canyon depths, we're talking about extreme values, those special points where our functions reach their highest or lowest points. Up, down, and all around. Now let's imagine we're riding a horse through a mountain pass. We come to a spot where the path ahead goes up on one side and down on the other. This is kind of like a saddle point. In calculus, a saddle point is a point on our function where it looks like it could be both a maximum and a minimum, depending on which direction you look. It's like being at the top of a hill, but then realizing that you're also at the bottom of a hill on the other side. Saddle points are important because they help us understand the overall shape of our function, even if they're not the highest or lowest points. To find those amazing extreme values and saddle points, we need to look for special spots called critical points. Think of critical points like clues that mathematicians use to solve the mystery of where our function is changing direction. Here's the secret. At a critical point, the slope of our function is either 0 or undefined. It's like when you're at the very top of a roller coaster. For a brief moment, you're not going up or down, you're just there. To find critical points, we use a powerful tool called the derivative. But don't worry, it's not as scary as it sounds. The derivative is just a fancy way of finding the slope of our function at any given point. Section 5, the second derivative test, a detective's tool. Once we've found our critical points, we need a way to figure out if they're maximums, minimums, or saddle points. That's where the second derivative test comes in, like a detective's magnifying glass. The second derivative tells us how the slope of our function is changing. If the second derivative is positive at a critical point, it means the function is curving upwards like a smile. That's a minimum. If the second derivative is negative, the function is curving downwards like a frown. That's a maximum. And if the second derivative is 0, well, that's a clue that we might have a saddle point on our hands. Section 6. Example. Finding a mountaintop. Let's try an example. Imagine we are hiking and we want to find the highest point of a mountain. We can use math to help us. Say we have a function that describes the height of a mountain. This function will help us understand the shape and the peak of the mountain. The function is f of x equals negative x squared plus 4x. This equation represents the height of the mountain at any point x. To find the mountain's peak, we need to find the maximum value of this function. This is where the mountain is the highest. First, we find the derivative of the function. The derivative helps us understand the rate of change of the function. The derivative, f prime of x, is negative 2x plus 4. This new function will help us find the critical points. Then we set the derivative equal to 0 and solve for x. This will give us the points where the slope of the function is 0. So we solve negative 2x plus 4 equals 0, and we find that x equals 2. This is a potential peak. This is our critical point. A critical point is where the function could have a maximum or minimum value. Now we need to use the second derivative test to confirm if this critical point is a maximum. The second derivative is f double prime of x equals negative 2, which is negative. A negative second derivative indicates a maximum. This means our critical point is indeed a maximum. The mountain reaches its highest point here. So, the mountain reaches its highest point at x equals 2. This is how we can use calculus to find the peak of a mountain. Section 7. Example. Spotting a saddle point. Now let's imagine a different function, g of x, y equals x squared minus y squared. This is a classic example used in multivariable calculus to illustrate the concept of a saddle point. This function describes a surface with hills and valleys. Imagine a landscape where some areas rise up like hills and others dip down like valleys. Let's see if we can find a saddle point. A saddle point is a point on the surface where the slope changes direction. First, we find the partial derivatives, partial g over partial x equals 2x. This tells us how the function changes as we move along the x-axis. And partial g over partial y equals negative 2y. This tells us how the function changes as we move along the y-axis. Setting them equal to 0, we get x equals 0 and y equals 0. This is where the slopes in both directions are 0. This is our critical point. A critical point is where the first derivatives are 0, indicating potential maxima, minima, or saddle points. Now, for the second derivative test, we need to find the second partial derivatives. Partial squared g over partial x squared equals 2. This tells us about the concavity along the x-axis. Partial squared g over partial y squared equals negative 2. This tells us about the concavity along the y-axis. And partial squared g over partial x partial y equals 0. This mixed partial derivative tells us about the interaction between the x and y directions. Plugging these values into the formula for the discriminant, we get d equals 2 times negative, 2 minus 0 squared equals negative 4. The discriminant helps us determine the nature of the critical point. Since d is negative, we know we have a saddle point. A negative discriminant indicates that the critical point is a saddle point. So at the point 0, 0, our function has a saddle point. This means the surface curves up in one direction and down in the perpendicular direction, resembling a saddle. Section 8. The extreme value theorem guaranteeing our success. Here's a secret weapon for finding those extreme values, the extreme value theorem. This theorem tells us that if we have a continuous function, no jumps or breaks, on a closed and bounded interval, like a section of our graph, then the function is guaranteed to have both a maximum and a minimum value within that interval. It's like knowing that if you're walking on a closed loop trail, you're bound to encounter both the highest and lowest points along that trail. The extreme value theorem is a powerful tool that assures us we'll always find those extreme values as long as our function and interval meet certain conditions. Section 9. Applications of extreme values and saddle points. Extreme values and saddle points aren't just abstract mathematical concepts, they have real-world applications. Engineers use them to design bridges and airplanes, economists use them to analyze markets, and even video game developers use them to create realistic landscapes and movements. For example, imagine you're designing a roller coaster. You'd use calculus to find the maximum and minimum points of the track to ensure a thrilling but safe ride. You'd also need to consider saddle points to create those moments of weightlessness and excitement. So the next time you're on a roller coaster, remember the math behind the thrills. Section 10. Conclusion: Mastering the Mountains of Calculus. Congratulations, explorers! We've climbed the peaks of extreme values, navigated the valleys of minimums, and even conquered the tricky terrain of saddle points. We've learned how to find these critical points using derivatives and the second derivative test, and we've even unlocked the power of the extreme value theorem. But our adventure in calculus doesn't end here. There are many more mathematical mountains to climb and valleys to explore. So keep your curiosity alive, your pencils sharpened, and your minds open to the wonders of math. Section 11. Now it's your turn. Practice makes perfect. Ready to test your skills? Try finding the extreme values and saddle points of these functions. 1. H of x equals x cubed minus 3x, and 2. K of x, y equals x squared plus xy plus y squared. Remember, practice makes perfect. The more you explore the world of calculus, the more confident you'll become in tackling even the most challenging mathematical peaks.